Good morning, everybody, and welcome to room C313. We now have up Richard Jones to talk to us about microservices.
Thank you, Justin. Now I'm going to have a bit of an experiment here. I'm going to try doing this without my glasses. So if I start rambling, it's because I'm old and I can't read. Alrighty. So I've been a Python developer for over 2 decades now. And recently I've been getting into microservices in kind of a big way. At the very first PyCon AU, I think it was the first one, I actually gave a talk about doing microservices using micro frameworks, and that was fascinating at the time. But it's only in the last couple of years that I've been getting into like dozens of microservices to support a business. And so this talk is pretty much the things that we've learned as a team over that 2 years, that journey. So I work for Reese, and we have an IT system that is itself decades old, and it's grown to support a business that's been around for almost 100 years. We have some pretty unique business processes, so it's kind of there's some interesting stuff in it to work on, and it's a bigger IT department than you probably think for a plumbing supply company. But what even are microservices, I hear you ask? So, you know how your huge organically growing code base resembles something akin to a bowl of spaghetti? Well, the term spaghetti code is probably something you're familiar with. Well, microservices are kind of like a bowl of spaghetti with meatballs. There's slightly less mess, little blobs of order, and it's very tasty. Anyway, that's microservices. So, these are the things that I'm going to be talking about today. Roughly speaking, a bunch of different subjects. Things that we've run into, and things that we've learned along the way. So, just to give you some sort of context, the architecture that we've implemented. We have a Kubernetes cluster managing dozens of microservices in Java and Python with Angular front ends using the BFF pattern. Can I get a hands up who's heard of the BFF pattern? There's a few of you. Okay, I'm going to come back to that though. We do also have a monolithic Gennaro application. Who's heard of Gennaro? Frankie, good on you. My co-worker in the audience. And we have a single Intermix database underlying it all. Now this one's probably a bit more popular. Who's heard of Intermix? 5, 6, excellent. I hadn't heard of either of them before I started at Reese. Interactions between our services in that cluster are verified through contracts, which I'll come back to. So the services are loosely domain-based, so there's one for users and one for customers and so on. And they're all loosely coupled, supported by these contracts. We have users internally at our branches. There's about 800 branches in Australia and New Zealand. And they use a suite of Angular and Gennaro applications on their counter computers. We also have the general public accessing our public websites. I think we've done a pretty darn good job of successfully operating this bilingual environment because we've ensured those services are loosely coupled and interactions are supported by those contracts. An individual Python service looks like this, roughly speaking. It's a Docker container and it has Django running in it under ModWSGI, and it uses Django Rest framework. That's the DRF there. It's a very long name though. We run over Intermix, that's the database, and we use PyODBC to interface to that, and we have a Django InfmixDB interface for Django, which we maintain to run specifics for the Intermix database. Calls to all of our other services are encapsulated in API libraries. We don't embed calls to our other services in our services using requests directly. We encapsulate them so that we can have consistent and robust handling of inputs and errors as appropriate. We're not just copy and pasting a particular version of a call to another service across our code base. Those libraries sit over a common HTTP layer that we maintain based on requests, which has additional common features like request tracking ID and authentication. It also has some other bells and whistles that I'll be coming back to. In some microservice architectures, front ends, the user interfaces, are not allowed to talk directly to services or the database, but must instead talk through proxy services, and these are called backends for front ends. The merit of this is debatable, and I'm happy to talk about that after the talk, but this is the pattern that we've implemented across the board. So the architecture of a Python front-end app is similar to a back-end app, to a service. It has the Docker container with the Django operating as the BFF, but aside ModWSGI, we have the Angular code, which is served up by Apache as well. We still run those calls to the services through the API libraries, but you'll note there's no connection to the database. So one of the big wins that we found in our teams is the use of Git submodules. So when we're using those libraries to connect to those services in our organization, we've found it super convenient to be able to work on the service that we're working on and the API library connecting to the other service at the same time. Using Git submodules, you can pull in a library repository into a service repository, pinned to a specific commit of the library repository. And then you can work on that code at the same time, making changes to both code bases. PyCharm has excellent support for this, allowing us to perform effectively a single commit and push, resulting in all of those repositories that have been affected being committed and pushed at the same time. This prevents the need for making a release of the library, getting it slightly wrong, making another release of the library, pulling it into the service, updating the service, and so on. Significantly speeds up that development cycle. Consistency of environment and practices basically means folks are able to help out other teams or even migrate between teams with minimal impact to their productivity. This means things like code style, development tooling, testing methods, and project structures. We had an almost clean slate to work with. At Reese, we were training up existing Django developers to work with Python. So when I joined, we were developing all of these practices from the ground up. So some of the common tooling that we've settled on include things like Cookie Cutter, which ensures that all of our services start off looking similar. And I'm quite serious. We, in the team, just the team that I work in, we've got a couple of dozen services that we look after. That's a couple of dozen service code bases. And they're all stamped out to look exactly the same in structure. So for example, they all store the Django project information, like the settings file, in a module called main. That's across the board. Everybody knows exactly where the settings file is, regardless of which service they're looking at. We use Tox so that developers don't have to worry about managing all of those virtual environments for all of those services. We use PyTest because it's just best in class for a long time now. We use Flake8 and iSort so there's no really weird surprises about any of the formatting of the code. More recently, we've turned on Black in our projects to just format the code for us. We're also using iSort again, just to automatically format the code for us. That was inspired by our experience using Prettier, which is a tool for front-end development. So it automatically formats TypeScript and HTML and CSS. A big win of doing this, of having this common approach to all of these services, means that if we come along and we have some tech that involves, look, we've just got to bump up the timeout for our database connection across all of our services. We can just code a script that makes that change across all those repositories and pushes up that change, and we don't have to do any work. So that's a huge win for us. Funny story, after I'd written that slide, a couple of days later, Hawkeye posted this to Twitter, which pretty much lists exactly the same tool set that I just listed. So I think that's probably a bit of a win. Just a little word about testing. We've had a bit of to and fro in our teams about how to approach testing. Melanie Crutchfield yesterday described very wonderfully in her talk about how you can find a dozen different definitions of what a unit test is, let alone even the other types of tests you might encounter. In our team, we've had that conversation. We still have ongoing conversations about what end-to-end means. We aim, though, for our unit tests to be as high as possible in our code as they can be, while still achieving our coverage goal, which is 100% coverage, with caveats around things that are difficult to test. That means that changes to our underlying implementation, or refactoring, generally won't break those tests. And indeed, we can use those tests to ensure that we have confidence when we do refactoring and we haven't broken anything. PyCharm was introduced for consistency of editor across our newbie teams. It allows everyone to help out other people doing work on their computer or helping them out with things they're getting stuck with in the editor. It's especially useful when we're doing pair programming. Our developers routinely use the introspection tools that PyCharm provides to poke around implementations. Other editors are an option for the more experienced developers, of course, but the Vim folks are quite jealous of multi-cursor editing. So we did have a few teams that were migrating to Python. So we learned it in stages, team by team. And it's a really big win. I can't overstate this. Having those folks who are Genero developers, which is a very niche language, and its future is debatable, being trained up in a language that certainly does have a future, that's a huge win. But we did it in stages. So one team could kind of forge the new path and help inform the practices in other teams. In practice, what happened was things were a bit too new, and some things worked, like encapsulating our calls to services in libraries to share common code, using those contracts, and some things didn't. One team in particular found Tox very difficult to use, and they ended up replacing it with a complicated bash script and Docker Compose. That's introduced its own knock-on issues. The takeaway here really is that if you're going to do this, you need to force yourself to have regular, consistent meetings, events, whatever, where you touch base with those teams and find out where their pain points are and catch them early. So we run services and consumers of those services in 4 different programming languages in quite different stacks of software. So how do we make them work together? I've touched on the use of contracts. We use pact to declare and enforce contracts between our services. This allows us to avoid the need for expensive and brittle integration tests. Integration being front end all the way through to a database, where the database is in some known state. We can verify that a consumer's use of a service is valid and that a change to a service won't break registered interactions. Finally, we can use those contracts, the corpus of pacts, those contracts, to answer questions about how our APIs are actually being used. For example, to deprecate a field in a response payload, we know whether or not we have any consumers using that field. If you'd like to know more about pact, then you can either chat to me after this talk, or you can watch my colleague Sylvia Yap's talk from last year's PyCon AU. Along the way, we've developed a version of pact called Pactman, which is a play on words. The other options were worse. We've released it as open source. It's a pure Python implementation of pact mocking and verification, and includes some really solid PyTest support. So if you're going to get into pact in Python, this is the go-to tool. Another aspect of interoperability, you've got contracts up here talking about services talking to services. Another level of interoperability is all the way down at the HTTP layer. So generally, HTTP talks to HTTP pretty well because it's been around for quite some time. But we found one big sticking point. What you're seeing here is a thing called HTTP Keep Alive. And it removes the need for closing and reopening of connections from consumers to services when the consumer knows it's going to make multiple requests to the same server. And that's very common in a microservice framework. The time taken to manage that connection can often equal or even exceed the time to service requests. So the problem we ran into was we were using uWSGI, which is very popular, but unfortunately it doesn't implement Keep Alive. A client believes that HTTP Keep Alive is active, but when it sends through a follow-up request, uWSGI has closed the connection, and we get an error. Normally, folks run WSGI applications behind another server, like Apache or Nginx is very popular. And so this isn't a problem, because Nginx will just smooth out that little bump. It'll see that the connection has been closed, and it'll open a new connection, and the connection works. We, however, are running a microservice architecture where services talk directly to other services in a closed environment. We don't need Nginx. We can just poke them straight at each other. Or we thought we could. So we ended up going through a rather painful process of replacing uWSGI in our implementations with ModWSGI, which I've already mentioned is the current WSGI implementation we use. And that definitely does implement Keep Alive. So there are so many different ways that computers can fail, even just temporarily, and we need to build a little resilience into our services to cope with that. In a microservice architecture, you're more susceptible to brief, random, intermittent, inexplicable errors somewhere in the OSI stack. There's lots that can go wrong. These propagate into our code base as TCP errors, or client disconnected, or HTTP 502 proxy failures, or the driver did not return an error, which is the worst case. So we've implemented a few things to work with this. One of the things we've done is turn on retrying of certain types of HTTP errors. So our underlying HTTP library implements retries, a certain number of retries of HTTP 502 errors and TCP level errors for GET requests. We also see errors sometimes when we try to connect to the database for a number of reasons. So we've added retries in our Django database layer to retry those database connection attempts. With those two things in place, which were reasonably simple to implement, we found our rate of reported service errors drop dramatically. One little tweak to the database one, though, is that the Intermix database that we connect to can actually take some time to connect, in the order of seconds in the worst case, but hundreds of milliseconds sometimes. We want pretty rapid responses, generally speaking, to our service requests. So for that reason, we hold on to the connection to the database for a pretty long time. The network can have other ideas, though, or the database might be restarted overnight, resulting in spurious errors from our services when they next try to use that connection. So we've implemented a validation step in our database connection so that we perform a kind of select one from dual effectively. A database no-op, it goes to the database, makes sure that connection is still alive. And that's actually a win from our environment where we've learned about that from our Java teams. This is a feature that's built into the JDBC client that they use in their code. So on the subject of resilience, we monitor the health of our systems on a per-team Grafana dashboard. We actually have a physical screen per team hanging from the ceiling that we can display these dashboards on. These display information about error and retry rates over the day. The very top graph up there, service anomalies, that graphs for all of our services how many unexpected HTTP codes, status codes we saw. Unexpected being anything that's not a 200, a 300, a 400, some of the 400s. If we see a 500, you'll get a spike there. So that shows us that we saw one of those today, well, when I took this photo. If we see a bigger number there, then we know that we've got a problem. And we have had instances where we've seen a spike of 50 or 100 in that anomaly graph, and we've gone off to the network people and they've said, oh yeah, look, something was happening. We also show things like response times for high load services and other information like build statuses, Sentry alert counts, and so on. All of our services send all of their exceptions, all of our front ends for that matter, send all of their exceptions to Sentry. They're not lost, and you wouldn't believe the number of exceptions happen in a JavaScript front end. We also use ELK, that's Elasticsearch and Kibana, and Prometheus to collate log events and performance data. And there's a custom tool sitting behind this to pull in data from other places like Sentry, our build system, our Git repository, our packed broker, and our Kubernetes cluster. And that just shoves it all into a Postgres database that Grafana can pull in. So you can see up here the build statuses and so forth, but over the other side there, outstanding pull requests. All logging is sent to a central Elasticsearch aggregator and is done using JSON so that we can perform intelligent queries on our logged events. This is again looking for anomalies in services, any log status that we don't expect to see. So, one big gotcha in the Pythonic world is if you deviate from the community default tech stack norm, your life becomes difficult, just because you're out in the wilds that very few people have been before. Again, coming back to who's heard of Intermix? The Python world really likes Django over a fully controlled Postgres database, for example. Just dealing with the connections to the Intermix database has been interesting in itself. We've had to create that Django database adapter. The actual initial work was done for us by Common Code, but we've then since taken it over and we run that open source project now ourselves. We found so many weird issues in ODBC connections and so on. So this is the Django Intermix DB project. So we run that single shared legacy obscure database. But Django, it's got its own thoughts about databases. It wants to store its own data, things about users and sessions, and there's a couple of other things in there as well. We can't do that in the legacy database because we have dozens of Djangos. That would mean we'd need a second database. 2 databases in Django is basically a bad idea. It causes all sorts of difficulties. The configuration is a bit messy, but as soon as you start thinking about doing anything around transactions in your unit tests, you are screwed. Fortunately for our services, the Django database, users and permissions and sessions and all that other stuff, is actually unnecessary. So we just don't initialize it. That means we get this warning every time we start up Django saying, hey, you've got unapplied migrations. It's like, yeah, whatever. So there's a catch there, though. The Django Rest framework has this really nice HTML view. It's kind of like Swagger, but it's not Swagger. And you can see basically the REST interface that you're exposing to the world, and you can do requests and stuff. Unfortunately, it really wants Django auth to be a thing. And if you don't have Django auth, it just breaks. So what we did was we just ignored that and put in another version of Swagger, and we're happy. The catch, though, is our front-end apps actually are authenticated. They're externally authenticated. We have a separate authentication token that comes into them via Kerberos magic. So we run a little dummy SQLite database in those because they don't need to connect to the real database. We can just store that effectively transient user information just in an SQLite database, and that's good enough for us. Oh yeah, so Django, again, opinionated about databases. It really needs an identity column. We did have to add some identity columns to our database, some of our database tables, and that's just a thing you have to know. It's going to happen, and you can't work with tables that have multiple column primary keys. That's just not going to work. We do have a need to process big jobs without impacting our microservices. Typically, I would just add celery. Just add celery, right? But you would just use celery because there's a lot of prior art out there, and it integrates pretty well with Django. By default, though, celery really wants to use RabbitMQ or some other message queue or the Django database. Now, we don't have a Django database. We weren't going to get RabbitMQ installed. Redis wasn't around yet, so we did use uWSGI spooling for a while. It has two issues. One, uWSGI, I've mentioned already, but two, that stores the queued information on disk in your container in Kubernetes that has wonderful ideas about, no, I'm going to just kill that container and start a new one. So that was not going to be a good idea long term. We ended up using ActiveMQ for queue processing because it's a supported message queue in our environment. Unfortunately, ActiveMQ ain't so popular in Python world. So there is some libraries, but they're not very robust. So we ran into some issues there. So that's a thing. RabbitMQ, quite popular. Redis, very popular. Go with those if you can. We really should have pushed harder to get the Redis installed sooner so we could use it. Excuse me. The final thing I'd like to touch on is performance. So this generally hasn't been an issue because we've restricted most services to a smallish domain over 1 or 2 tables, just serving up the data, and a 20 to 40 millisecond response time is just fine. Our complex services, though, run response times of 400 milliseconds for a single request. And we'd be getting requests for hundreds of responses at a time. That math comes out at tens of seconds for responses, and that's not good. So we used various tooling to investigate hotspots in our less performant servers. The Django debug toolbar and Silk, which is another plugin for Django, are super valuable for this. We also used some custom profiling logging, just logging timestamps in our code. And we used a little bit of New Relic distributed tracing, but to be honest, nobody really knows how New Relic works. We already knew our more complex services could be hitting dozens of tables and half a dozen downstream services when calculating their responses, but the profiling gave us the solid numbers to work with. Silk is cool because it does code profiling as well as database profiling, and it can work with non-GET requests, whereas the debug toolbar is limited to GET requests and some POST requests. It's a bit of a hack. What you're seeing here, though, is the debug toolbar because I'm profiling a GET request. It's super nice to see. So, as I said, we already knew we were probably doing a bad thing. We had new teams, and our focus was on getting it implemented right, not necessarily getting it implemented in a most optimal way. We could work on the optimization later, and that's what we're doing now. So in this case, just on the SQL, we can quickly see that we have a ridiculous number of SQL queries. Does it say 201 duplicate queries over 4 seconds? So just a little bit of investigation, and the debug toolbar gives you the tools for doing this. I highly recommend you poke around in it. You can click on any one of those queries and see the exact code that's causing that query to happen. So we went in and did that, and we reduced it down to 50 milliseconds over 4 queries. So probably preaching to the Django choir here, but reducing the number of SQL queries was critical to us getting those services' performance up to speed. For a consumer displaying a large customer order, for example, though, we still need the ability to price hundreds of items. So what we do in our services is we provide batch interfaces. It allows the consumer to price 100 items at once in one REST call. That allows us to reduce the network overhead keep alive would help us there. But it also allows us to squash all of those requests down into optimized SQL queries as well, which keep alive isn't going to help us with. Batching is kind of a no-no in REST land, but I say stuff those guys. Caching is also done at various levels in our services to reduce the fan-out damage caused by large requests. Thanks to the fan-out and sometimes back-in again nature of microservices, some services can be hit a stupid number of times during a normal processing day. Caching by consumers of calls to one service, one endpoint, reduced it from about 40,000 requests per minute to 4,000. And this is the simplest caching of all. The LRU cache function is provided in the Python standard library. Here, we're taking advantage of the fact that information about our branches doesn't change over a day. So in our services, they just have to request the information about a particular branch once, and that'll be held onto for a day, and the next day we'll get it afresh. We are looking at other solutions for caching, which would allow us to have shared managed cache dedicated to a set of workers, but that's a whole other step that requires things like cache invalidation, messages being sent around, and other fun things. The last thing I'd like to talk about is, as a Python developer, I've kind of taken for granted the ability to jump around the source code of whatever I'm working on. Is the REST interface doing something odd? Jump to the source of the Django Rest framework, and so often we had to do that. Or even Django underneath that. If the database layer is throwing weird errors, jump to the Django layer. Jump into the C source code of PyODBC. We've done this a number of times. And you get answers. You can file bugs, you can file pull requests and get things fixed. That open source ecosystem is very easy to take granted until it's just not there, which is something we've run into in our Java programs and our Genero programs in particular. We just have to guess at what's going on. So support open source. That's, I think, all I have time for, so thank you.